Good morning, everyone, and good morning, sir. In this lesson, we'll discuss the magnetic quantum number, also known as the third quantum number. Magnetic quantum numbers, an integer that expresses the component of the quantized angular momentum of an electron, atom, or molecule in the direction of an externally applied magnetic field. Magnetic quantum number, generally symbolized by M, denotes the orientations of the electron's orbital with respect to the three axes in space. Its symbols look like this. The magnetic quantum number describes the energy levels available within a subshell and yields the projections of the orbital angular momentum along a specified axis. The value of ME range from negative to E with integer step between them. The S subshell E equals 0 contain one orbital, and therefore the ME of an electron in an S subshell will always be 0. The p subshell E equal 1 contain 3 orbitals, in some system depicted as 3 dumbbell-shaped cloud. So the E of an electron in a p subshell will be negative 1, 0, or 1. The d subshell E equal to contain 5 orbitals with ME value of negative 2, negative 1, 0, 1, and 2. The value of the ME quantum number is associated with the orbital orientation. The magnetic quantum number further divided this subshell into the orbitals and tell us about the orientation of these orbitals in space in relation to the other orbitals. Knowing about this tell us more about an electron and its location within an atom. There are different possible values from the magnetic quantum number depending on the angular momentum atom number. The number of orbitals can be determined from the angular momentum quantum number L, and the possible values of ML can be determined from the following equation. And according to the information provided by the table, from L equals 0, there's only one possible orientations because there is only one value from ML. From L equal 1, there are 3 possible orientations because there are 3 values of ML. From L equal 2, there are 5 possible orientations because there are 5 value of ML. And for L equal 3, there are 7 possible orientations because there are 7 values of ML. Magnetic quantum number orientation. From the S subshell, L is equal to 0, there is only one possible orientation of the orbital. Since there is only one value of the magnetic quantum number, which is 0, the only orientation of S will look like this. From the p subshell L equal 1, there are the 3 possible orientation of the orbitals since there are 3 values from the magnetic quantum number, negative 1, 0, positive 1. The 3 possible orientations will look like this. And from the d subshell L equal 2, there are 5 possible orientations of the orbitals. Since there are 5 values from the magnetic quantum number, negative 2, negative 1, 0, positive 1, positive 2. The 5 possible orientations will look like this. And from the F subshell L is equal to 3, there are 7 possible orientations of the orbitals. Since there are 7 values from the magnetic quantum number, -3, -2, -1, 0, +1, +2, +3. The 7 possible orientations will look like this. Questions. First question is how to find magnetic quantum number. Quantum numbers in general and magnetic quantum number in particular can be derived while solving the Schrödinger equation. However, boundaries or constraints need to be put in place to match the equations with the physical world. The magnetic quantum number can be derived from solving the azimuthal equation of hydrogen Schrödinger equation. And next question, what? Those the magnetic quantum number determined. The magnetic quantum number primarily determines the number of orbitals and the orientation of the orbitals in a given subshell. Consequently, it is dependent on the orbital angular momentum quantum number, also known as the azimuthal quantum number.